Hello, good morning students. Today we are going to discuss about digital communication. Why we are going for digital communication? Because we are having analog communication, right? But now why we are going for digital communication? Mainly, if you go for analog communication, so there is a chance of noise is occurring. So to overcome the noise using analog communication, it will be very difficult for us. So if you go for digital communication, it is very less to remove the noise when compared to the analog communication. Okay, and also why we are going for digital means whenever the aging of the components is occurs, if you perform an experiment using analog components, after aging of the components, we'll get the faulty values. If you perform same with the digital communication, even though the aging is occurring, we can able to get the accurate values. That's why we are going for the digitalization. That is digital techniques. Okay. Today we are going to discuss first introduction to digital communication. Okay, so any communication means it is nothing but exchanging the information between the persons or anything. A transmitter will be there and a channel, and it will be a receiver. The channel acts as interface between the transmitter as well as receiver, right? That is the concept. Now we go for what is the block diagram of digital communication. Okay, in this class we'll study what is the block diagram of digital communication. Okay, so what is that communication system? It converts an information into electrical signals which is required for the transmission. Okay, that is analog systems, they are going to convert analog messages into signals which can be propagating through the channel. Okay, what are the elements of digital communication system? We see this. What are the elements of digital communication system? What are the elements? The source encoder, source decoder, channel encoder, channel decoder, receiver, modulator, channel demodulator. These are the main building blocks of digital communication system. Do you know, right? Source means it is responsible for getting the information. Actually, the information at present should be in analog form only. Even though we are talking about digital communication system, the input we are going to take is analog signal only. Okay, here the input signal is in analog form, so which is applied to the source encoder signal. What is the source encoder signal does? It will convert that analog signals into equal samples. Okay, it is going to convert the analog signal into equal samples. Okay, and converting equal samples, it is passed through the channel encoder. The channel encoder, it will not accept the analog signal values, so we need to convert the analog signal data into binary data form. So the channel encoder, it will accept the only binary data form, which is applied to the modulator. As you are aware of that, what is the modulator does? First it will take the message signal, then which is applied through the channel. So through the channel, whatever the data we are getting, so first we are taking the information in analog signal, which is converted to the digital signal with the help of source encoder. The channel encoder accepts the data which is applied to the modulator, then through the channel it will reach to the demodulator. So what is the demodulator does? Whatever the data it is taken by modulator is applied to the channel decoder. The channel decoder accepts the data from the whatever the data given by channel encoder, which is applied to the source decoder. The source decoder again converts digital data into the binary form, which is reached to the receiver. Okay, so the channel encoder and decoder acts as a key role while accepting the data from source and given to the receiver. They are playing a key role. The channel encoder simply assigns extra redundant bits for the purpose of security. That extra redundant bits will be only understood by the channel decoder. While sending it to the receiver, it will remove that extra redundant bits. Okay. That is the block diagram about digital communication. See, what is that? The source of information here. We said, right, the information should be analog or digital. Because we are talking about digital communication, the signal should be in analog. So we need to convert into the digital signal with the help of our source encoder technique. See, in digital communication, the signal produced by the source is converted into the digital form, which consists of ones and zeros. Okay. So for that, we use output transducer at the receiver side. Okay. So the communication channel would act as a medium between the transmitter and receiver. Okay. And it should be affected by white Gaussian noise channel. Okay. See, we said, right, what is the use of source encoder? It will simply converting the output of analog signal or continuous signal into the digital form that should be understood by the channel encoder. Okay. Then what is the source decoder? If analog signal is required, so source encoder tries to decode the analog signal. Okay. Then channel encoder. Whatever the information which is passed through the channel encoder, the use of channel encoder is to remove the redundancy or noise which come from the input signal. That's the use of channel encoder. Then the channel decoder, it will able to reconstruct the original message signal which is given by the source. Okay. Then we said, right, the modulator simply maps the input bits and producing the corresponding waveform. Okay. So why we are going for digital communication means simply we can able to regenerate the distorted signal back. Similarly, we can able to, with the help of regenerative repeaters, we can eliminate the noise. Okay, and provide the error-free signal. That is the use of digital communication. Now we are going to discuss the digital communication first system, which is, what is that? Pulse code modulation system. What is that? Pulse code modulation system. What do you mean by pulse modulation? Basically, what is the pulse modulation means? In pulse modulation, the message signal is a low frequency signal, whereas the carrier signal is always a pulse train. Okay. Then how do you define pulse code modulation? Means nothing but the pulse modulation which is used for transferring the analog information, okay, which is continuous speech or data. We already said that in pulse modulation, the carrier is a pulse train. So what is my pulse modulation? Some parameters of carrier signal, which may be amplitude or pulse time or pulse position, which is varied in accordance with the instantaneous value of modulating signal. We call that as pulse modulation. Then what is it by pulse code modulation? Nothing but we take the PAM signal, nothing but pulse amplitude modulation signal. That is, the amplitude of pulses will be varied in accordance with the message signal. We call that as PAM. So the PAM signals are quantized. So the PAM signals are quantized and then coded. We call the technique as pulse code modulation system. What is that? The PAM signals are first quantized and then coded, which give rise to a technique we call as pulse code modulation system. Let us see what is the block diagram of pulse code modulation. See, what is that block diagram? Having two parts: transmitter path, transmission path, and the receiver path. Okay. See, we said, right, already the input signal we are taken is a continuous message signal which is applied to the low pass filter. So what is the low pass filter? It will allows all the low frequency components. Let us assume we are assuming the frequency of having W hedges. The low pass filter allows all frequencies within the W hedges and does not allow the frequencies above W hedges. So let us consider the input signal is x of t. So x of t is band limited to W hedges, which is applied to the sampler circuit. So what is the use of sampler circuit? Nothing but, which is also called as here sample and hold circuit. Simply it converts the continuous signal into equal samples at a rate of Fs. What is Fs? Which is nothing but sampling frequency. Here we have to choose the sampling frequency such that twice the highest frequency component of the message signal in order to avoid aliasing effect. Okay. So what is the output of sampling circuit we are getting? So we are assuming the input signal as x of NTS. Sorry, we are assuming the input signal as x of t. So after the sampling, we are getting the signal as x of NTS. What is that? We are getting the signal as x of NTS. So x of t is the input signal and x of NTS is the sampled signal. That is the sample signal, like how the value is continuous in time, sorry, continuous in amplitude but discrete in time, like 2.2, 5.8, 6.9, like that. That is the output of the sampler circuit. Okay. So x of t, x of NTS, then which is applied to the quantizer unit. So what is the output of quantizer signal? Nothing but this. We are getting the output of sampler values are these values, like 2.2, 5.8, 6.9, like that, right? So we are going to get the fixed values. The 2.2 is rounding off to 2, then 5.8 is rounding off to 6, 6.9 is rounding off to 7. Okay. 6.9 is rounding off to the 7 values. These are the values we are going to acquire. So we call that values as xq of NTS. What is that? We call that values as xq of NTS, which is nothing but the output of quantizer. Okay. Which is nothing but the output of the quantizer values. We call that as the output of quantizer values. We call that as xq of NTS. So where we are getting the fixed amplitude values. Okay, that is 2, 6, 8, because from the continuous input signal. So we need to convert this 2, 6, 8 to the binary data format. We need to convert that into the binary data format. Okay, that is the responsible for encoder. What is the encoder does? It should convert the fixed amplitude levels into the binary data form. So, and it will assign the bits also. So suppose the input is 2 received by the encoder. So let us assume it is a 3-bit data. So which is 0, 1, 0. So for 6 it is 1, 1, 0. For 8, 1, 4, 1, 3 zeros. Like that it will assign, because the source encoder data, that is binary data, which will the binary data which is coming from the encoder. Okay, that is the input data which is applied to the encoder. So the output of encoder is in binary form, that is V digits. What is that? V bit of data, which is applied to parallel to serial converter. So that is the complete data, like we assume, right, 2, 6, 8. So they're all coming in the parallel form. So we need to convert to the serial data, so which is applied to the parallel to serial converter. Then we get the output of PCM signal as like this. See how the output of PCM signal means. See, I will show you. The output of PCM is whenever there is input bit 1, it will be amplitude, input bit 0, no signal, input 1, that is nothing but binary data 1, it should be represented with the pulse. So binary data 0, no pulse. Like this, you will get the coded data. That's why pulse code modulation. Here 1, 0, 1, 0, 1, 0, 1, like that. There should be binary coded data. The information should be in binary data format. Okay, which is the use of pulse code modulation. What is that pulse code modulation? First, it will receive the analog data. Okay, then consider the input signal as x of t. The x of t is nothing but input signal which is applied to the low pass filter, which will allow all frequencies limited to W hertz, and above W hertz which will be eliminated. Then it is applied to the sampler circuit. It will convert that continuous signal into equal samples based on the sampling rate, which is applied to the quantizer. The quantizer convert the sampled values which are continuous in amplitude, discrete in time, into fixed amplitude and fixed discrete in time, discrete in amplitude, which is applied to the encoder. The encoder converts that data into the binary form, which is applied to the parallel to serial converter. Then we get the output of PCM data. Okay, after that, what is that? The transmission path, because we are getting the PCM signal here, which is applied to the channel. So the channel will be adding some noise. Okay, so we can get the distorted PCM which is applied to the receiver. So before applying to the receiver of the PCM, we are applying to the regenerative repeaters. What is the use of regenerative repeaters? It will be having equalizers and amplitude shaping pulse circuitry. So what is the use of that equalizers? Means equalizers remove the noise which is suffering from any amplitude distortion and retrieve the original PCM output back. That is the use of regenerative repeaters. Finally, here noise-free PCM generator, noise-free PCM signal is given to the regenerator circuit. Okay, so that is the binary data information, that is 1010, which is applied to the decoder. The decoder converts the binary data into its sampled values, like 101 means it should be 5, then 1000 means it should be 8, that values. Okay, converting binary data into the its fixed amplitude levels, which is applied to the reconstruction filter. Okay, then we are getting a normal continuous signal. So whatever the input we are applying, that will be retrieved at the receiver unit, nothing but the destination unit. Okay, that is the use of PCM transmitter as well as receiver. Okay, we said, right, assume the input signal is x of t or w of t, which is limited to b hertz. The sampling rate is twice the highest frequency component. Okay, then what is the bandwidth of PCM, which is assuming n into b. Bandwidth of PCM is n into b. Okay, what are the advantages of PCM? Which is very inexpensive when compared to certain techniques, and it can be easily multiplexed, and it is easily regenerated, and it will provide better noise performance. The signals can be reconstructed easily. Okay, but the one disadvantage is it requires wider bandwidth than the analog signals. What is that? It requires wider bandwidth than the analog signals. Okay, that's the PCM. Now we'll see what are the problems related to the PCM techniques. See, let us see what are the problems which will be related to the PCM. This one is my handwritten notes. Okay. Before that, let's see what are the formulas related to the pulse code modulation for doing problems based on it. Okay. You just now have seen, right? The pulse code modulation transmitter, pulse code modulation receiver. Okay. Then we'll see, let the quantizer, it will use as V number of binary digits. What is that? It will use V number of binary digits in order to represent each levels. So the relation between the number of bits and the quantized data, which will be given by Q equals 2 power V. What is that? Q represents the total number of digital levels of Q level quantizer. V is nothing but the number of binary bits. Let us example, if V equal to 3 bits. So we will be having 3 bits. How many total number of levels? There should be 8 levels. That means starting from 0, 0, 0, 0, 1, 0, 1, 0, like this up to 0 to 8 levels. Okay. Each sample is converted to V bits. Okay. Similarly, what is the sampling rate in PCM formula? Which is small r equals V into Fs. We know, right? What is in by V? Nothing but the number of binary bits. V represents the number of binary digits. Fs means the sampling rate. We know, right? The sampling frequency, which should be twice the highest frequency component of the message signal. Okay. So the formula for transmission bandwidth of PCM is bandwidth, which is denoted as B suffix T, which is greater than half into R or greater than 1 by 2 into V into Fs. From this formula, see, these are the main three formulas. Relation between the quantizer and number of binary digits, which is Q equals 2 power V. Then the sampling rate in PCM, which is R equal to V into Fs. Then the transmission bandwidth required for PCM, that is D suffix T, which is greater than or equals 1 by 2 into R. Okay. Those are the three important formulas for doing the problems using pulse code modulation technique. Let us see few problems related to the pulse code modulation. And also one more thing, the signal to noise quantization ratio. Okay. What is it by signal to quantization noise ratio? The ratio of signal power to the noise power, which is called as signal to quantization noise ratio. Okay. Higher the signal quantization noise ratio, so lesser the noise. Okay. So what is the signal to noise ratio for PCM signal means? This is the formula. See this one. Signal to quantization noise ratio for PCM signal is 4.8 plus 6 volts. S by N dB, which is less than or equal to 4.8 plus 6 V into dB, which is signal to noise quantization noise ratio of PCM. Similarly, another formula, signal to noise ratio for a sinusoidal signal, which is S by N dB equals 1.8 plus 6 V. Okay. This for signal to noise ratio in PCM. This for signal to quantization noise ratio for linear quantization. Okay. For PCM, remember this formula. What is that? 1.8 plus 6 V. Okay, we'll see the problems. Wait a minute. I will show you. See, this is the PCM output. We said, right, the continuous analog signal is applied to the sampler. So output of the sampler is the continuous in amplitude, discrete in time, which is applied to the quantizer. We get the fixed amplitude levels. So after encoder, it is converting into the binary data. The output of PCM should be like this. Okay. See the problems. They have given a television signal which is having a bandwidth of 4.2 megahertz. What is that? We are going to transmit a television signal that is providing a bandwidth of 4.2 megahertz using PCM system, and given that the number of quantization levels is 512, what we have to find? We have to find the code word length, the transmission bandwidth, final bit rate, and output signal to quantization noise ratio. Okay, we need to find the code word length, right? Transmission bandwidth, we know, right? Transmission bandwidth, which is BT greater than or equal to 1/2 into R, where R is nothing but the sampling rate. So R equals V into Fs, the sampling rate in PCM, the code word length. Okay, then output signal to quantization noise ratio. See, first write the given data. So a television signal having a bandwidth which is FM equals 4.2 megahertz, and they said quantization levels which is Q equals 512. So what we need to find? We have to find the code word length. Okay, we need to find the code word length. We know, right, the relation between number of quantization levels and the V number of digits, which is Q equals 2 power V. So what is the Q given? Quantization levels 512, which equals 2 power V. To solve that, we need to apply logarithm term on both sides. So we are getting the V. What is that V? Code word length or number of binary digits. So V equals 9 bits. Okay, then what is the transmission bandwidth formula? The transmission channel bandwidth, which is V into FM. What is that? V into FM. What is V? V is nothing but the number of binary data bits V. FM is nothing but the binary bandwidth, which is 9 into 4.2 megahertz. So which we getting 37.8 megahertz, right? Then final bit rate, which is nothing but the sampling rate. What is the formula for sampling rate? Sampling rate equals R equals the signaling rate, which is R equals V into Fs. What is that? R equals V into Fs. What is V? The code word length, nothing but number of bits. So V into Fs. That is, V means 9 into Fs means the sampling rate, which is 2 into FM, right? That's why see, Fs greater than or equals 2 into FM, 2 into 4.2, which is 8.4 megahertz. Then the signaling rate in PCM is R equals V into Fs. V is the number of digits, that is 9, into FM is 8.4 megahertz. So totally we are getting 75.6 megabits per second. Okay. Then finally the transmission bandwidth, which is greater than or equals 1/2 into R. So we know that the value of R. So we're getting the value as 37.8 megahertz. See, first we are finding the code word length. How to find the code word length? So by taking the relation between the quantization levels and the V number of bits, that is Q equals 2 power V, that is Q equals 2 power V. They have given the data as Q as 512 and we need to find V. So by taking log on both sides, we'll find the V as 9 bits. Then we are finding the transmission bandwidth. There is nothing but bandwidth which is greater than or equal to V into FM. Okay, we know the value of V and we know the value of FM. Then we are finding the final bit rate, which is also called as signaling rate, which is R equals V into Fs, where Fs is twice the message signal frequency. From this we find the Fs. Then finally we'll find the signaling rate Rs by the formula V into Fs. Then transmission bandwidth final formula is half the signaling rate in PCM. So we get as 37.8 megahertz. Then what is the output signal to noise ratio for PCM signal? We said right previously, which is less than or equal to 4.8 plus 6V. We know the value of V as 9. Okay, so we get the value as S by N as 58.8 dB. We get the value as 58.8 dB. Okay, like that. We see another problem. 24 voice signals are sampled. See, what is that? 24 voice signals are sampled uniformly. They have to time division multiplexed. The highest frequency component of each voice signal is 3.4 kilohertz. If the signals are pulse amplitude modulated using Nyquist rate sampling, what would be the channel bandwidth required? And if the signals are pulse code modulated with an 8-bit encoder, what would be the sampling rate? The bit rate of the PCM system is given as 1.5 into 10 power 6 bits per second. We know, right? If they are using time division multiplexing, the bandwidth should be, because they are shedding 24 voice channels. So let us assume if n channels are time division multiplexing, then the transmission bandwidth is n into FM. We know, right? FM is nothing but 3.4 kilohertz. They have given the highest frequency component. So because they have given 24 voice channels, so that's why bandwidth equals 24 into 3.4. Then what is the signaling rate? We have to find the signaling rate. What is the signaling rate? Which is R equals V into Fs, right? The signaling rate equals R equals 1.5 into 10 power bits per second. Okay, like that we'll find the sampling rate. Okay, then we'll see another problem. A PCM system uses, a PCM system uses a uniform quantizer followed by a 7-bit binary encoder. A PCM system uses a uniform quantizer followed by a 7-bit binary encoder. The bit rate of the system is equal to 50 into 10 power 6 bits per second. What is the maximum message signal bandwidth for which the system operates satisfactorily? What we have to find? What is the maximum message signal bandwidth we need to find? And then we have to find calculate the output signal to quantization noise ratio when a full load sinusoidal modulating wave of frequency is applied to the input, which is applied to the input. Okay, which is applied to the input. Then see, let us assume the message signal bandwidth should be FM. Then we know, right, the sampling frequency is twice the highest frequency component of the message signal. Fs is greater than or equals 2 into FM. They have given the 7-bit binary encoder. So the number of bits is V equal to 7 bits. So the sampling rate in PCM, which is R equals V into Fs. So R equals V is 7, Fs is 2 FM. Okay, and they will provide the bit rate, which is nothing but the sampling rate or signaling rate in PCM as given 50 into 10 power 6, right? So R is 50 into 10 power 6 greater than or equals 14 into Fm. So Fm value should be 3.57 megahertz. And they said calculate the output signal to noise ratio when a full load sinusoidal modulating wave of frequency 1 megahertz is applied. So we said, right, whenever the modulating wave is sinusoidal, the S by N ratio is given as 1.8 plus 6V. So which is 1.8 plus 6 into V is given as 7. So we should be 43.8 dB. It should be 43.8 dB. Okay, like that. So we see another problem. The information in an analog waveform having a frequency FM is 3 kilohertz is transmitted over M level PCM system where the number of quantization levels is M equal to 16. Then the quantization distortion is specified not to exceed 1% of peak to peak analog signal. What we need to find? We have to find maximum number of bits per sample and minimum sampling rate which is required. So first write the given data. The total number of quantization levels M equals 16, nothing but Q equals 16. We know the relation between the number of quantization levels and the binary bits V. So which is Q equals 2 power V. Okay, that is Q equals M equals 16. So 16 equals 2 power V. By applying log on both sides, we get the V as 4 bits. And we know that the maximum frequency component FM equals 3 kilohertz. So we know the sampling frequency Fs greater than 2 into Fm. So which is 6 kilohertz. So what they said, we have to find the bit transmission rate, which is also nothing but signaling rate in PCM, which is R equals V into Fs. Okay, we know the value of V, which is 4 bits. We know the value of Fs, which is 6 kilohertz. So finally, what is the bit rate? R equal to 24 into 24 kilobits per second. Okay, like that they will be asking for a few marks. Mainly they will be asking find the sampling rate in PCM, find the quantization levels in PCM, find the signal to quantization noise ratio in PCM. They are asking those problems very frequently. Okay, so this is about the PCM techniques. Mainly they will be concentrating on signaling rate in PCM, which is R equals V into Fs, and the transmission bandwidth Dt is greater than or equals half into R, where R equals V into Fs. Okay, mainly they'll be concentrating on 4 formulas: the relation between quantization levels and V number of bits, Q equals 2 power V, and transmission bandwidth in PCM, Bt greater than or equals 1 by 2 into R, and signal to noise ratio 1.8 plus 6V. Okay, these are the main they are concentrating. And next we go for matched filter. What is meant by matched filter? What is meant by matched filter? First of all, what is meant by filter? What is meant by filter? Filter is nothing but it will allow the required components, okay, from the multiple. Okay, when many number of people are there, we need to select the desired people and eliminate the other people, which is nothing but the basic function of filter. Okay, what is the meaning of matched filter? Nothing but a matched filter is a filter which will able to allow the input signal and remove the noise to a maximum extent. We call that filter as matched filter. What is that? What is the use of matched filter? It is allowing the input signal properly and remove the noise at a maximum extent, which we call that filter as matched filter. It will we'll see that what is that matched filter? It is a device or a filter which is used for optimum detection of the transmitted pulses. We are assuming input signal is x of t, which is having g of t plus w of t. What is that g of t? See, g of t is the input signal and it will be suffered by noise. We consider the noise as white Gaussian noise, which is w of t. Finally, the input we are applying to the filter is x of t, which is x of t equals w of t plus g of t, which is the received noise signal over obtained to the time, then which is sampled at equal intervals. Then we are going to get the binary data after performing sampling. Okay, that's the matched filter. In the tomorrow class, we'll see the in detail about the matched filter. Okay, that is what is the properties of matched filter, then what is the impulse response of the matched filter. We see the problems regarding matched filter in the coming class. Okay, thank you.